if I record it. So I don't hear, no one's hitting me up in the chat saying they have any objections. So I'll go forward. Oh gosh. I want to make sure. Oh, okay. So it's just recording the Zoom session as it goes. All right. So attendance question today. Well, I probably don't want to record the attendance question. Oh well. Attendance question. It's a Monday, so we're doing an estimation question, right? So here is the estimation question. How many pieces of candy corn are in 1/4 of a cup? How many pieces of candy corn are in 1/4 of a cup? The reveal for the estimation question from last week was 600 sheets. There was 12 pads in this whole package of writing pads, and each pad has 50 sheets. Therefore, 12 times 50, 600. All right, that's our estimation question for the day. Is the candy corn. And we are working on day three of Unit 2, Consumer Credit, Lesson 3, Loan Calculations and Regressions. And we have our 2 learning targets. The first one is I can calculate the present value of a single deposit investment. And the second learning target is I can calculate the present value of a periodic deposit investment. This is all about you being able to figure out what a loan balance is as the loan is amortizing over time, right? It's that amortization table that we're looking at with these lessons. Okay, so give me an indication in participants, a little yes check mark or whatnot that you've got this day 3 up and you are ready to begin. Just looking at participants here. I'm looking for some sign or indication that you're good. You've got day 3 up. Good. I got one person saying they're ready. You know, kind of how I recommend this is if you're on your Chromebook, that if you don't maximize this window, you can pull any window that's not maximized over to the right or the left. And if you pull it all the way to the right or left and let it go, it will immediately become half the screen, right? So you could have Zoom going on. You can have Zoom going on over here and having me share my screen along with the lesson over here that you can work on yourself, and that way you can do 2 things at once. Another option, of course, is that you could have the Zoom kind of minimized in the corner, if you will. Or what's another thing you could do? Oh, you could have 2 devices, right? Like Yomari might have Zoom on her phone, or maybe she's doing the Google Classroom on her phone, and then she's doing the Zoom on an iPad, for instance. So 2 different devices. If you have a phone and don't mind using your data and that kind of thing, you can do it that way. So there's a couple different ways of making this work for you. Put down your name where it says your name on your copy there. All right. You may review, if you wish, the math topics for Unit 2 or the plan of study. Again, we're on consumer credit. We're almost done. We have credit cards and then 1 lesson after credit cards, right? We got credit cards and average daily balance. So we are on day 3 of loan calculations regression. And okay, so last lesson, I needed you guys to understand some exponents, and what I needed you to understand what a logarithm was, because we dealt with natural logs. We used natural logs to solve a problem with a variable in the exponent last time. And now, in order to get you guys to understand regressions, we need to talk about functions. To understand regressions, we need to talk about functions. And I know you guys know a lot of this already, so a lot of this will be review. That's okay. Review is good sometimes. Okay, so functions. Here's a great graphic with lots of different functions here. This horizontal line is called a constant function. Why is it a constant function? Because, oops, sorry. I apologize for that. That's my little motion detector. This is a constant function because nothing's ever changing, right? It's just staying horizontal. It's not going up. It's not going down. It's a constant. It's just one number all the time. You find out what the value of y is for any given x, and it'll be that same y value for every other value of x, right? Okay, then we have our favorite Algebra 1 function, the linear function. Now this is the y equals mx plus b stuff, all right? The y value is equal to the slope times the x value plus the constant, or b, which is the constant, right? This is actually a special linear function called the y equals x function, right? It's this diagonal line here that if x is 5, y is 5. If x is 1, y is 1. So it's like whatever x is, that's what y is. This is the y equals x function. We saw that as the little line of reflection that distinguishes an exponential function from a logarithmic function, right? This little y equals x line was the line of reflection for the parent function for an exponential, which is then the reflection. The logarithm is the reflection of that. Whew, okay. Then we have our quadratic. Our quadratic is either our smiley face or a frowny face, right? A quadratic can either look like this, where it's like a little smiley face, or it can look kind of like flip this upside down where the arrows are pointing down, and it can be a frowny face, right? That's our quadratic. That's our x squared plus b squared equals c squared thing, right? Where we have various coefficients in front of those numbers, and this gives us the different shapes of quadratics. But if it has this general shape of a smiley face or a frowny face, that's a quadratic, all right? Then we have this function family here. This is called a cubic function, Now, you probably didn't look at these in Algebra 1, but maybe in Algebra 2, you should have seen at least a couple of these, right? These cubic functions, they have this kind of shape. It kind of goes up and kind of goes, crosses the y-axis at some certain point. And, you can move this around all over the place. There's all sorts of translations we could do with this cubic function. But this is the general shape of a cubic function. All right, then we have our absolute value function. Our absolute value function is a little bit like our quadratic, except now it's like two different linears, right? What's going on here is that it's a linear function coming this way until it reaches some point of absolute value, and then it will change and go the other direction, right? So you have either a V shape or an upside down V, right? It can be upside down just like the cubic or the quadratic can be upside down as well. Okay, then we have our square root functions. They're going to look like this, all right? I don't know what you want to call this, but this is a square root function. It's this general shape. Why does it end here? Because we can't, find square roots of, negative numbers unless we're going to talk about imaginary numbers. All right, so that's why it kind of stops right there, because the square root of -2 would be like, what two numbers multiply together to be, what two numbers that are the same number multiply together to be -2? Well, a negative, you'd have to have a positive and a negative, which means you don't have the same number. So that's why it has to end right there at the origin, because there's some square roots you can't take without playing with imaginary numbers. I don't think we're going to deal with reciprocal functions, but this is the shape, right? They have these, it's like two things. Whenever you see these arrows, remember all the arrows and all these functions means this function goes to infinity and beyond, right? To take the Toy Story motto there of Buzz Lightyear. Exponentials look like this. They have this little L shape. They can also have the other direction. They can go down. So you can have exponentials going up. You can have exponentials going down. Keep in mind that even though it appears to like touch this axis here, it never does. It gets infinitesimally small. So infinite means like, it's infinitely big. Well, infinitesimal means, infinitely small. So, I mean, this line will never, ever touch that axis, even though it appears to, just because it gets so small. And then here's our logs. Here's our logarithm function that we learned about last time, which is really like the inverse, right? It's like the mirror image of our exponential. Again, this line right here will never touch this axis. It'll just get infinitesimally close. Okay, that's our basic shape. So this is easy. We need to train our brains, do some pattern recognition. All right. So what do you think? What kind of function is it? What kind of function is it? I will take suggestions in the chat. What kind of function is this? You can, of course, go back and refer to your different kinds of functions poster. Just in general shape, in the chat, tell me what kind of function this is. And it's a multiple choice. You've got 7 different choices to choose from. And no one has hit me up in the chat with this yet. You can direct message me if you like, or you can just
linear.
Linear. Thank you, Cayman. Yes, indeed, it is a linear function. Linear function. Thank you. All right, these are not trick questions, people. These are not trick questions. Okay, what do we think this one is? What do we think this one is? Again, you can refer to that poster. What kind of function is this? What shape does it have?
Like an S or a 5.
What was that?
Like a S or a 5?
Answer for five? What?
No, like you asked me what it was shaped like.
Yeah. What's it shaped like?
Kind of like an S, like a snake.
Oh, like an S. I see what you're saying. Yeah, like a yeah. Well, I mean, if you go back up to this poster,
I
which
said right here,
right here, what?
cubic, right next
Cubic.
to
Thank you,
value.
sir. Absolutely, right? Here's our cubic shape, right? And that's what this has right here. That's a cubic shape, right? We choose cubic there. All right, that's our cubic shape. Good. Okay. You guys, if you guys took Algebra 1, you looked at a lot of these. A lot of these in Algebra 1. What shape is
Quadratic.
quadratic? Cayman, you're coming to our rescue. Anybody else do want to do any heavy lifting other than Cayman? Cayman's doing great. Absolutely. Quadratic. This one's a smiley face. It could be a frowny face. Let's look at this next one here. What do you think we've got here? What kind of function?
Exponential,
Yeah,
you say?
exponential. Yeah, exponential. Exponential.
Exponential.
Absolutely. It's got this shape right there. And if we go back to our poster from the very beginning, right, here's our exponential shape, right? Absolutely. Great. Again, we're just doing some review of what our function family is, because here's what a regression is. A regression is when we have all these little dots, we get all these little scatter plots going on, and we got to determine what shape do those dots kind of remind us of? What kind of line can we run through these dots to give us a function shape? So that and why do we want a function? Why do we want to do a pick a function to kind of match the shape of the dots? It's because once we choose a function, we can start to predict where the dots aren't, right? We can start to say, well, if there was a dot over here, where would it be based on the function of the pattern? So what kind of regression analysis do you think is going on here?
Quadratic.
Very good. It's a quadratic regression. It's got that quadratic shape. Oh, okay. We got all these little scatter plots
Linear.
and linear. Too easy, right? Too easy. Oh, do I have a solution for this
A cubic.
one? this one This one is probably quartic, which I don't think I had on. I don't think I had that on the list that for you guys to know. This is gonna be like a quartic regression.
Okay.
Um, that's all right. I didn't have that on the poster. Don't worry about this one. So even when I looked at that, I was like, okay, that's gonna be some kind of polynomial. That's gonna be something bigger than a quadratic. It's gonna be bigger than
That
a
looks
cubic.
like that might be if it goes down, it would be like a cosine function.
Oh, that's true. Yes, yes, it could be. All right. What about this one here? This one here.
I
Now, there's
thought it
actually
was
this could
exponential.
yes, that's what I would choose too. Keep in mind that yes, our data, which could say this could be exponential, right? It does have that nice curve shape. An exponential does. It also could be one half of a quadratic too, couldn't it? Right? It could be like there could be another, like if we were to extend the data out, it might a quadratic might also model this shape fairly well. I'm gonna have to remember to make that another possibility. Okay. All right. Why do I want us to pause here? Oh, I probably wanted you guys to do these on your own, but we kind of go. Can you go over? All right. Do you want me to? Is the person asking me to go over these again? Someone's Desmond's asking in the chat. What do you need, Desmond? We have a constant, which are these the functions that don't change. We got linear functions that are straight that change. We've got quadratic functions that have this U shape, either a U shape like this or an upside down U shape. We got these cubics, which have this kind of, I don't know what you want to call this, call it an S shape or something. As Cayman said, absolute values have these V shapes, square root functions, reciprocal functions, exponentials, which have this kind of curve that kind of goes all the way up or goes all the way down. And then we have the logarithms, which are like the exact, like mirror image of an exponential. I still don't know what Desmond is asking me. Can I go over? If you want to just assess this. we need, if we're going to talk about regressions, again, all these here are regressions, right? This is, if we want to call this an exponential regression, we're starting to look at this and we're starting to say, okay, all these little dots form a shape. And that shape could probably be described as an exponential function. And the handy thing about this is that once we do a regression for this exponential function, we could then start making predictions. Well, where do you think the next dot's going to be over here past at 200, right? At 200 might be somewhere over here where, well, it's going to be somewhere up here, right? This line kind of, I'm feeling like this shape would keep going up, and this allows us to make predictions. And when we can make predictions, we can make plans. And when you can make plans, it usually has to do with money, right? You're usually making plans. Like you might say, oh, I noticed that my sales go up in the sale of swimsuits goes up in June. People buy swimsuits and swim gear in June. Well, then you can start to make predictions about how many swimsuits you need to order and stock in your store in order to be able to sell and meet demand. So we need to talk about fit, right? So we can do regressions even when the fit isn't particularly good, right? If these are our 6 dots, yeah, we could maybe do a linear regression that kind of suggests, well, maybe we could predict that the data would be along this line. But notice how the dots are really nowhere near the predictive line. That tells us this is a bad fit. This particular selection of dots, this linear function is not the best fit for this scatter plot. Whereas if the dots were a little closer together, lined up a little nicer, we would talk about this as a regression with good fit. And if every single one of those dots are right on our line, we could talk about perfect fit or near perfect fit. So there's this idea of fitness. And the fitness is how well the model, which is the line or the function we've chosen, fits the actual data. The more residual, the more that this line differs from that scatter plot dot, right? The more this dot is the distance between the line and the dot. That's the residual. The wider that gets, the more the fit is a bad fit. The shorter the distance of the residual between the dot and the line, that is a better fit, right? So tell me, looking at the fitness of this regression analysis, what's the fitness? Is it a perfect fit? Yeah, it's near perfect, right? I'd say perfect to excellent. The line is right on those dots. What about this one here?
Bad fit.
I wouldn't yet call this one a bad. I could say I would say okay, meh to good, right? So it goes through two of the dots, but then I have this residual for 2 of them as well. So I would say this is good to meh. It isn't like if those 2 dots weren't on the line, we could start calling this a bad fit. What about this one? Hours versus percentages.
Good.
Yeah, I could actually absolutely call this good. I might even want to start calling this excellent because I don't have really hardly any outliers. This is pretty. I would call this line pretty predictive. So I would say good to excellent. I would give you points for either one of those. That's good. It's definitely not a perfect fit, and it's definitely better than okay meh, right? It's not. It's definitely better than that, but it's not a perfect. Describe the fitness of this one here. All right. What about this one?
Okay, now that is a bad.
Okay. Yeah, I would think this one would be anywhere from bad to okay, meh, right? There's some predictive value here, but I got this guy who's kind of way out there. I got this one that's way out there. This line, may predict some data, but I could definitely see myself having, data outside that line. So this would be okay to meh or meh to bad. What about this one? The line, just so you know, the line is this black line right here.
You only got 1 dot on the line.
Exactly. Right. This is a bad fit, right? That linear there is not a good fit for this function. If I had to choose a fit, if I had to choose a function, I would choose some kind of polynomial function that went down here. I'm seeing one line going here that goes back up here and goes back down. I would think a quartic function might be able to match that, or like a cosine function. Like something's going on there. But I definitely linear does not fit this data. It's definitely a bad fit. All right. Oh, did I put this on twice? Okay, that's the exact same. That's the exact same data. My apologies. I put this on twice. Somehow that got in there. Okay. Describe the fitness of this one.
Excellent.
Yeah, I don't know. I mean, it's pretty good. It's pretty good. I don't know if I would go with excellent because I do have some issues here. Like this little dot there has quite a lot of residual. That dot there has quite a lot of residual, but it definitely good. I would say call it a good fit. I would definitely call this good. If you want to call it excellent, that'd be all right. It's definitely not a bad fit. It's definitely not a perfect fit. I think it's better than okay meh, right? I think it's better than okay meh. It is kind of giving us a nice prediction. Okay.
Yeah, we're not
Sorry.
even.
This is what is this? What's sorry, this made me laugh. This is a math joke right here. If you want to know what a math joke looks like, that's what it is. Is this a good regression line for this data? It is linear, right? The function we're looking for is linear, but it's nowhere near this linear, right? It's not this line. That's the okay, yeah. That's not a good fit, right? That's a terrible fit. That was you were hoping you're just looking at this. And you're like, yeah, a line should go right here. What's wrong with you? What are you doing with this blue line up here for? All right, bad fit. Oh, okay. What about this one?
Meh.
So yeah, I can get you where you're meh, right? Because the residuals aren't terrible here, right? They're not terrible. They're not so far from the line, but just looking at these dots, does it suggest to you that perhaps another function is needed? Right? Is linear the best choice for this data?
No.
Yeah, right. So like there's this, we don't want to, I mean, like, yes, can you choose a linear function for some of these? Yeah, you can. But I would look at like, well, let me think, a square root function. Sorry, I'm going to sneeze. Okay, I think I'm not going to sneeze anymore. What else could I use? Maybe like maybe this could be like 1/2 of a quadratic or something. This is not working for me. I mean, if you wanted to call this okay, meh, maybe, but I'm going to call this a bad fit. Me, I'm looking at this like, no, I need some other function. This is the wrong function to pick, even though I got a 1 dot on the line and the residuals aren't terrible. This is not the right function family for this one. Okay. What about the fitness for this one? We got this nice linear function here.
I say that's a bad too.
Exactly, right? The residuals aren't terrible, but this is not the right function to be picked. For this data, these little dots, we want like an exponential here, maybe, right? That's what I'm looking for. Yeah, the rest are so-so. That's a bad fit. So I want to give you this idea of a bad fit versus good fit. Oh, what do we say about this one?
Okay, that could be an excellent fit or a good fit.
Yeah, I would say good to excellent, right? I'd almost call this pretty close to excellent, right? That's that. But if you want to call it good, because there are a few, this one here's got some residual going on. Yeah, it's good to excellent. Absolutely. We are going somewhere with this. I promise. Let me quick look at where we are going. Whew, all right. I think we're going to end this early today. Let's just so we answered this last one. So this is what we started day one with. We started day one looking at this particular loan. The loan was $100,000, right? They're borrowing $100,000. The interest rate was 7.5%. The term was 15 years. They're going to repay this loan in 15 years at an interest rate of 7.5% per year. The loan was taken out in January 2010. They calculated the monthly payment to be $927.01. And this is called an amortization table, right? A payment schedule. Now, it doesn't go to the end of the loan. It just talks about the first year. But this is what the first year of that loan looks like. And again, I want to just point out some important pieces to this. One piece is that this person is paying back $927.01 every month. That's what they're paying every month. But you can break each one of those payments into the amount of principal that's paid and the amount of interest that's paid. All right. The amount of principal that's paid is how much money goes towards lowering how much is owed, right? If I take out my calculator, there we go. Yep. And I take $100,000 and I minus these 302 and 1 cent. Whoop, I didn't want that. 302 and 1 cent. There we go. $99,697.99. That's what we got going on right here, right? I don't know why I dropped the 99 cents for, but the loan went down exactly or should have come down exactly $302.01. The interest paid was going to be $625. The bank just gets to keep this. This just goes. This is just profit right here. All right. This first month you paid, so remember, of that $927, it's not like your loan, how much you owe is going down $927.01 per month. That's an important part to understand. What's happening is in the beginning of the loan, some of the money goes towards principal, and then in the beginning of the loan, almost 2/3 goes towards interest, right? And then each month, the amount that goes towards principal increases, right? In that first year, we went from $302 per month going towards the principal getting paid off to $323. That's just the first year. Remember, there's 15 years of this loan that's going to go on, and that the interest paid per month goes from $625 in the beginning down to $603 per month. So eventually, these things are going to flip. Towards the end of the loan, you're going to be paying about $600 towards principal on the 15th year and $300 towards interest. And what happens is, if we put this data of the loan balance, just the loan balance, just this data right here, into our calculators, we can create a scatter plot. And let me show you how that's done. So I'm going to clear this. I am going to go. I'm going to. I'll put it right here. No, I don't want it right there. I discovered that anything I put over here in the right-hand corner, that the Zoom kind of covers that up when I do Zoom recordings. So I would need to put this data table in my calculator, and here's how I'm going to do that. I'm going to press the stat button. I want to edit this list. All right, so I'm going to press enter. And I have these years. Now, my first thought was to make this in terms of 2010, 2011. If I do that, it kind of messed everything up. So I'm not going to do that this time. I'm going to put 0 in, right? I'm going to count. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many of these do I need? I need 12, don't I? Because there's 12 months. 11, 12. Or do I need more than that? There's my 10. Oh, I need 14, 13, 14. How did I know I needed 14? Because it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, I need 15 because there's the 0 on top of that. So let me add a 15 to this column. All right. I've got list 1 set up 1 through 15 for my data values. All right. This will make the calculator, it'll make it easier to find this data on the scatter plot. Then I got to put this data in my calculator, right? $96,248.64. I was about to complain that these periods are going to be longer now, but I'm liking this fact that we have a little extra time. Let's see, when does this class end? I'm looking at the news. Our new end time is 12:06. All right, I got plenty of time. We'll probably still end early. Oh, the 0 has to be 100,000. Mr. K, you want to explain what's going on, what you're thinking?
Yeah, when you do this, I mean, it would be technically 16, but you're not going to put the 0 at the end. In 2000, well, I mean, if you start, you want the starting value to be 0, so then it has like the starting value of 100, and then at year 1 you're going to put 96,249. At
96,249.
Yeah, you just put the numbers, you just scaled up. At 0 years, you paid nothing already. So you want a starting value.
Ah, so Mr. K is saying at 0, what I really want to, I don't want to model this exactly. What I'm going to do is I'm going to put 100,000 in here.
Mhm.
He's saying I can do it this way and then do 96, 248. Yeah, absolutely. I can do it that way. And that's fine. It wouldn't, it wouldn't change my regression that much if I did it the other way. Just keeping with the, but you're right.
No,
The starting value is important.
Well, no, I just want them to interpret that as like when things are being conveyed and stuff. It's telling you that after a year, the balance went down like 3,700. So yeah, what you're doing is you're just showing a different representation of it starting at 0. So then they can see the value as it goes down. In that table, it just shows the loan, the difference after each year that it goes down.
Okay. So I'm doing this is not fun work, I gotta admit, when you're just putting data in a calculator. This is why I like spreadsheets. It's so much easier to work with spreadsheets. But it is what this is what it is. And I don't like that it's rounding these numbers for me either. That's messing with my tracking. 67690101 and 60. 437
85.
85.
Next one is 536517. So 17. Yep.
Yep.
Next one is 46,262 and 84 cents. The next one is 38,339.72. And after 29,801.51 cents.
Thank you.
That is 20,600. 46 cents.
46 cents. Yeah.
And the last one is 10,685 and 11 cents.
Oop, I don't want 2 decimals. All right, and then do I want to add a 0 here?
Yep, you can do 0.
All right. All right. I'm a little worried because it all worked out and it shouldn't have. Did I miss something? Oh, well. If I missed something, I missed something. We added 100,000 here, which is new to the thing, and yet somehow everything worked out. And I'm just a little afraid that I skipped a number, which will just, what it'll do, it'll create a little extra residual here. That's no big deal, but I'm just, no, I feel like I did all right. Oh, well. Okay.
That's right.
Let's see. Now I got to work on my skills on this calculator. Okay, so I want to go into, let's see, is it second table set? No. Stat plot? Yes. Okay. Press the blue button and press the y equals. And because you press the second button, which is blue, it'll go into this menu called stat plot. We want to turn a stat plot on. All right. We want to turn the stat plot on. I'm going to press enter. I want to switch this over to on. All right. The type of scatter plot I want to choose is little dots. I want my X list to be list 1. That's why I made my, my 0 through 15 to be a list 1. And I want my Y list to be list 2. All right. If you don't know how to change lists, if you kind of look at these numbers here, you see L1 right above your number 1 on your keypad. It's L1 is in blue. If I wanted to put list 1 in here, I press the second button and list 1. And it'll put whatever list I want. If I wanted list 3, I could put list 3 in. But in this case, I want L1 and L2. I set it up that way. I am going to choose, I don't like the boxes. I'm going to choose little dots instead. Well, maybe I don't know. Yeah, I guess we'll stay with boxes because that'll make the line go through them. Okay. Once you've got this part, this is why I'm recording this video, because this can be the tricky part. It's all the little menus. Again, I pressed second, y equals, which got me into stat plot. I pressed enter to turn on stat plot 1. I had to move it over to on by pressing enter. All right. I went over to the type. Click down until I get to the type. I want this little dot. I want the dot type. I want, oops, I cleared it. Why did I do that? I'm going to try it again. There I am. I'm going into the menu. I'm making it on, I'm making it scatter plot. X list is list 1, Y list is list 2, and then my mark can be in the box. All right, once I have that, let's see if I can do this. I'm going to press graph. I'm going to cross my fingers before I do this. I'm going to press graph. Nothing happens. All right, this scares people, but you have to modify more things, right? There's more buttons to press, people. We're going to zoom. I know that the static plots are in there somewhere. So if you press zoom, I'll get this menu. I want to try this thing called zoom stat. Zoom stat. And there it is. See, the calculator chose the correct zoom setting to show all the dots on our calculator. And I will point out that this picture right here, right, this is what this is modeling. Notice how this picture doesn't have a box right here. That's Mr. K and I added this. This is our 10,000, right? Our 100,000, I'm sorry, our $100,000 mark at 0, right? When X is 0, they borrowed $100,000. So this is why this shape. So now we got to ask ourselves, what kind of regression would we choose for this particular window? Well, you could choose a linear, right? We could choose a linear regression, and notice how there's very little residuals when we choose that linear function. But as you've already learned, hopefully, that even though this linear function kind of, sort of fits the data, this is not the best model to use. All right. And let me kind of explain why. So once you've got your data in here, and your calculator can do some more magic for you, believe it or not, I'm going to press the stat button. Oh, stat button. And I'm going to have it run a calc. The first calculation I want it to run is a lin reg. That's linear regression. I'm going to have it run a linear regression on the data that I have in this graph. All right. Pressing stat, going over to the calc menu. I'm going to run a linear regression. What this is going to do for me, it's going to calculate that line. So I want my X list to be list 1. That's right. I want my Y list to be list 2. That's right. And everything else is fine. I'm not going to change anything else. I want it to calculate. I'm going to go down to calculate, press enter. And there we have something interesting. It's telling us that the linear regression for this data is Y equals A, which is negative 6,556, and then times X plus B, which is 107,721. That is gibberish to you right now. That's okay. Do you remember our friend Y equals? We're going to go into Y equals using these numbers. Now, I'm going to put them in the chat. I'm going to put these numbers in the chat. Negative, let me see.
I got you.
Okay, Mr. K is going to put these numbers in the chat for us. We use what A equals and what B equals. And then once I see that, because I am not good at remembering numbers, they will fall right out of my brain the moment I move to the next screen. All right, he's got A in there. B is 107,721. All right, we got it. Okay. Now I can go to Y equals. In Y equals, we can put functions in, right? You remember that from yeah. And remember that linear function has that Y equals mx plus b format. It's a coefficient of A. We have A is negative. I can even move my calculator a little bit. Is negative $6,556. And 0.9162. I probably don't need all these digits. It's going to be close enough, but I'm just going to put them all in for now. Okay, so that's my A, right? Times X. So I got to put my X variable in. Use this button up here to put X in there. Math brain, yeah. And then I'm going to add the B. So because it's mx plus b. Mx plus b is 107,721 and 2727. Okay. So I've got it in here just like that lin reg told me to do, right? It told me it's in that Y equals A times X plus B format. I got it in there. There's the A times X, right? There's my X plus the B. I'm now going to tell it this thing to graph, and look at that. It will graph me this line. This is beautiful. This is not, we didn't have these back in the day, these graphing calculators. This makes life nice. This makes life nice. This looks like a pretty decent, regression. But when I start zooming in a little bit, I'm going to start noticing the imperfections here, right? I'm going to notice the imperfections that I've got some residuals that are not as much as I want. And of course, we learned a second ago that we don't want to use a linear regression on data which clearly is curved, right? This data is clearly curved. So we're going to run a different kind of regression. We're going to run a different kind of regression. We're going to go to stat again, since we don't believe this regression is particularly good. We are going to go to, so I press stat, I go to calc. I'm going to run a quadratic regression, quad regression. I want the X list to be L1. I want the Y list to be L2. I'm going to go down to calculate. Woo, now, again, Mr. K, I'm going to need these numbers in the chat. What's this telling me? It's telling me that, got 5 minutes. It's telling me that the regression, if I was going to fit a quadratic function on this regression, that it would have this format. It would have these values for the A, the B, and the C, right? A, it's going to be of the format A times X squared plus B times X plus C, right? It's that X squared plus B plus C, right? So A is going to be equal to negative 242 and some change. B is going to be equal to negative 2,917. That's the value is going to go in there. And then C is going to equal to be $99,229. I think we round these to the nearest hundredths. We're probably pretty good. We don't need every single digit. All right, so I'm going to go into Y equals. And I'm going to go into Y2 just to put in a different, I wish these calculators had the color, but I'm just going to put it in this format, right? So A, I have it in the chat, is negative 242, sorry, 242. I'm going to round these to the nearest hundredths place. So, no, I want a decimal. 0.63. All right, times X squared, because it's a quadratic. And then it's going to be plus negative 2,917.47. Just rounding these to the nearest, and then it's going to be times X, right? Because it's B times X. And then plus C, which is 99,229 and 24 cents. All right, I'm going to press graph again, and now 2 lines are going to be graphed. But look at that line. That's just beautiful right there. When I zoom in on this, I'm going to notice that there's my linear, right? Isn't that nice? Look at that. I know this doesn't turn you on like it probably does, Mr. K and I, but like we like this. We like it when the regression line just hits that, and that's just, oh yeah, it's a good feeling. All right. I even was playing with cubic regression. A cubic regression is even better when you zoom in even more. Okay. But we're not going to go there. We are going to end it here. I'm sorry we didn't end earlier, in fact, but that's what I wanted to show you, that we can use our calculator, put these numbers in stat. We can create a scatter plot right on our calculators. We can run a linear regression or a quadratic regression, or whatever regression we want to do. We can stick those into Y equals, and we can have this all be graphed. And then you can take a picture of that with your device, and then we could turn that picture in for an assignment, right? That's what we're trying to get you towards, is this idea of what you're doing, some crazy cool stuff with regression lines and stuff. And again, this is some advanced stuff that you guys are ready for, that you guys can do. We will have some more on this later, but here are the two. Oh, look at that! I gave myself all that. You didn't have to put all that in the chat. I already given myself that. I already had the regressions ready to go. Okay, well, anyway, that's us. That's this period. When are we supposed to end? We're supposed to end in 3 minutes from now. I'm letting you out 3 minutes early if you wish me a happy Monday.
Yes, happy Monday, guys. Good.
Sorry I talked at you a lot today.
Nobody?
Nobody's gonna wish us a happy Monday? You've all tuned out. Cayman was on fire. I'm surprised he's not.
Well,
wish us a happy Monday already.
Yeah. Because
happy Monday, Yamari.
Happy Monday,
yeah, I
Yamari.
learned a lot in my algebra year.
Oh yeah, you relearned your algebra year?
No, no, I learned a lot from that year.
Oh, good.
Great.
A lot of this was coming back to you?
Yeah.
Good. Who'd you have? You want to put a shout out to a good math teacher who taught you a lot?
Mr. McCurry.
Mr. McCray. Oh, I like Mr. McCray. Oh yeah, he's great.
Yeah, me and him known each other for about like 5 years now since we
Oh,
first met in I believe school 16.
okay.
Good for you.
Yeah.
It always works out that way, Cayman. You always believe in a teacher, and a teacher pushes you further ahead. So that's awesome. Good job. Let's go. Come on, go.
Well, all right, Mister. Have a good Monday.
All right. Thank you, sir.
You too, Cayman. Oh, I thought it was relevant. Everything. I mean, it might have seemed like it was going at a different pace, but I think if they were paying attention, they got it. So, you know. So
Yeah, it was like I don't want to just throw regressions at them without any priming. So I'm like, okay, I need to spend some time on function families and fit.
Well, that's what blows my gaskets when you might be able to stop the recording.
Oh yeah, I will stop.
Yeah. No.